So here I have an acid-base problem, and in this we're going to discuss a few things such as pH, pKa, and the Henderson-Hasselbalch equation. We have in this scenario sulfurous acid. It is a weak diprotic acid, diprotic meaning it has two hydrogen ions it can give up, and they have pKa values for the first one is 1.9 and the second one is 7.2. And the first thing we want to do is write an equilibrium reaction between sulfurous acid and its conjugate base in water. And sulfurous acid, H2SO3, will react with water to form, in its equilibrium, so we use the double arrow, its conjugate base and hydronium. Now, it is diprotic, so the conjugate base can also act as an acid, and there's a second reaction where it reacts with water to give us the sulfite ion and hydronium as well. So those are the two reactions for each of the acids that would be present. This one is the first hydrogen released, so this would be the pKa1, and this is the second hydrogen released, we call that pKa2. Now the next question is, if the pH is 8, which would be present at a higher molar concentration? The HSO3 or its conjugate base, the sulfite ion. So we're looking at pKa2 now. At a pH of 8, would I expect to have more of the right side or the left side? And the way we do this is by looking at the pKa. Generally speaking, if the pH is greater than the pKa, you're going to have more of the conjugate base. If the pH is lower than the pKa, then you're going to have more of the acid. In this case, 8 is greater than 7.2, so we would expect to have more of the base present, which is the sulfite. And the way you can kind of determine that is by the Henderson-Hasselbalch equation, where pH equals pKa plus the log of the conjugate base over the acid. And so basically, at a pH of 8, and pKa here is 7.2, if you were to solve for the ratio of A minus and HA, you would find that that would be a value that is greater than 1. In other words, we would have more A minus compared to HA, more conjugate base compared to acid. Another way to think of it would be if you have equal parts of HA and A minus. So if I had equal parts of my acid and my conjugate base, if that was a 1-to-1 ratio, the log of 1 is 1 or 0. So that part will drop out, pKa equals pH. In other words, when the pH equals the pKa, you will have equal parts of the two species. However, as we increase one of those, for example, if we increase A minus, the conjugate base, this number gets larger, and so the pKa plus that number will be greater than the pKa. However, if we increase or have greater concentration of our acid, the log of something less than 1, that is going to be a negative number, and the pKa plus the negative would be lower than the pKa value. So that's how you do these. You essentially look at the pKa value, look at the pH, and decide pKa, is it greater than or less than the pH, or you can think of it as, is the pH greater than or less than the pKa? So at a pKa of, or pH of 8, it is greater than our pKa, so we will have more of the base side. Now looking at the other example, if the pH was 2, so now we're looking at this scenario here, the lower pKa value. We want to know, would there be more H2SO3 or more H2 or HSO3 minus? And my apologies, I need to correct that right there. That should be a 3. So pKa is 1.9 for this first pKa value. If the pH was 2, that is greater than my pKa value, meaning I'll have more of the conjugate base, not the acid. At a pH of, let's say, 1, the pH less than the pKa, you would have more of the acid, less of the conjugate base. So that is how you solve problems where you have to determine if you're going to have more of the acid or the base. You compare pH and pKa, and we kind of derive our answer from the Henderson-Hasselbalch equation. Keep in mind when you have polyprotic acids have more than one hydrogen present. Each one can be released, and each one of those has a specific pKa value.